Hello everyone, let's continue the chapter hydrocarbons. So from the session of alkanes, the last topic is conformations. Okay, so today we'll see the topic conformations of alkanes. So what is this conformations means? We know in case of alkane, the carbon atoms were connected by C single bond. Okay, there exists carbon-carbon single bond in case of an alkane. Since it is a sigma bond as well as it is a single bond, it can be rotated. This carbon-carbon bond present in the alkane can be rotated, and thus different forms of same compound can be obtained. Thus obtained species are known as conformations, or which can be also called as conformers or rotamers. That means it is obtained by the rotation of carbon-carbon sigma bond. That's why which is known as rotamers. Okay, so please note down the three names: conformations or conformers or rotamers. How it is obtained? By the rotation between carbon-carbon single bond. Okay, and this, even though we can rotate this and different rotamers or conformers can be obtained, but that rotation of carbon-carbon sigma bond is not free. Okay, simply we can't do that rotation. There exists an energy barrier. There exists an energy barrier between this CC single bond, and that energy barrier is known as torsional strain. What is it called? That energy barrier between, that energy or that restriction we face when we will rotate that carbon-carbon sigma bond, which is known as what? Torsional strain. Okay, so normally in case of an alkanes, this energy barrier, that is this torsional strain value, is in between 1 to 20 kilojoule per mole. That value is in between 1 to 20 kilojoule per mole. It will vary from different alkanes, from ethane, propane, butane, like it will vary for different alkanes, but that range will be 1 to 20 kilojoule per mole. Okay, and for our syllabus, the given one is conformations of ethane. We should learn conformations of ethane. Okay, so ethane, we know its formula will be C2H6. Ethane, its formula is C2H6. That means there exist two carbon, right? There exist two carbon and three hydrogen atom. So this carbon-carbon bond is single bond, so which can be rotated, and we will get corresponding different conformations. And here also there exists a torsional strain, and that value for ethane is 12.5 kilojoule per mole. The torsional strain between carbon-carbon bond in case of ethane is 12.5 kilojoule per mole. Generally it is in between 1 to 20 kilojoule per mole. Okay, and thus when we will do this rotation of carbon-carbon sigma bond in case of ethane, we will get two conformations. Okay, or two rotamers will be obtained in case of ethane, and that conformations are called staggered conformation and eclipsed conformation. Just to see, the two conformations that we will obtain in case of ethane is eclipsed and staggered conformations. Okay, that means there are two structures are possible by the CC bond rotation. Okay, and this eclipsed and staggered conformations of ethane is represented by two different projectional formula. One is Sohor's projection formula and Newman projection formula. These are the atoms which is made by different scientists. That's why they are known as Sohor's projection and Newman projection. Okay, so what they have done is, in their own manner, they have represented the conformations of ethane which is obtained by the CC bond rotation. So first let's see the Sohor's conformation of ethane. This is very important, so you should know how to draw this Sohor's and eclipsed conformations of Sohor's and Newman conformations of ethane. In both case, if it is Sohor's or Newman, there exist two conformations, staggered and eclipsed. Okay, first let's see Sohor's conformation. So in case of Sohor's conformation, you can see a straight line which is tilted slightly towards the left side. Okay, sorry, tilted slightly towards the right side. This is represents the CC bond. Carbon-carbon single bond is represented here by using a straight line which can be tilted either to the right side or to the left side. Okay, and these three lines which represents the hydrogen atom. So how Sohor's represented the first conformation, eclipsed conformation. This is the eclipsed conformation of Sohor's projection that he has given to the molecule ethane. So like this, carbon-carbon bond is represented with a straight line and hydrogens were represented like this. And this is called eclipsed conformation. And the second one is known as staggered conformation. When you analyze this both projections, you can see a minute difference is there. Between the arrangement of hydrogen atom, there exists a minute difference. But you can see here, carbon-hydrogen bond. This is one carbon-hydrogen bond and this is also one carbon-hydrogen bond. So the distance between carbon-hydrogen bond is less in case of eclipsed conformation compared to that of staggered conformation. Distance between carbon-hydrogen bond is less compared to eclipsed conformation in case of staggered. Sorry, that distance is less in case of eclipsed and that is more in case of staggered. Okay. And second attempt was made by Newman projection. So using Newman projection, how we will represent the conformations of ethane. So here it is represented in this circular manner. There exists 6 hydrogen in case of ethane. So the front carbon is represented like this, which carries a space between the three different hydrogen, which is in a bond angle of 120 degree. So this is the front carbon. So from this front carbon, the 3 hydrogen goes and there exists a rear carbon. And that hydrogen atom is represented with this blue lines. Okay. And this is the eclipsed conformation of Newman projection formula. Eclipsed conformation of Newman projection formula of ethane. Okay. And this is the staggered conformation. And here the rear carbon, you can see the rear carbon and its hydrogen array. This is front carbon and the back there exists a rear carbon. Okay. So that rear carbon's hydrogen is these blue lines, and just to see the difference in the arrangement, even there also carbon hydrogen bond which there existed more space compared to this eclipsed. Okay. So that is the major difference between eclipsed conformation and staggered conformation. Here carbon hydrogen bond is more close, but here there exists a little more distance. Okay. So this is the concept, conformations of ethane or conformations of alkane, which arises by the carbon-carbon sigma bond rotation, and which is not free. There exists a torsional strain. Okay. And out of this eclipsed and staggered, which is more stable? Staggered conformation is always more stable than eclipsed conformation, because in case of eclipse, already I told you the carbon-hydrogen bond which is more close. Okay, which is more close. So there exists maximum repulsive forces and thus high energy. So energy high means stability will be less. But in case of staggered conformation, that repulsive force will be less. Therefore, energy also less. Energy less means stability will be more. So out of eclipsed and staggered, always staggered conformations are stable than eclipsed conformation. Moving to the next topic, that is alkenes. Okay. So alkenes means we know they are hydrocarbon which contains carbon-carbon double bond. That means they are unsaturated hydrocarbons. Okay. Alkenes are unsaturated hydrocarbon. And we know in a double bond there exists one single bond and one pi bond. Okay. And the speciality of pi bond we know, which is not much strong compared to the sigma bond, which is a weak bond, pi bond. So of course, in order to form a bond, there exists, or we need 2 electrons. To form one chemical bond, we need 2 electrons if it is sigma or pi. So the electrons which constitute this pi bond is known as pi electron. Okay, electrons which constitute pi bond is called what? Pi electron. And the speciality of pi electron, they are loosely held. Pi electrons are loosely held. That means they are available for the chemical reaction. This pi electrons are available, or they are loosely bound means which can be released very easily. That's why this alkenes are known as nucleophile. So children, you know what is nucleophile and what is electrophile. So since they are electron rich species, alkenes are electron rich species due to the presence of this loosely held or loosely bound pi electrons. Okay, so that is why this alkenes are also known as nucleophile, or they are known as electrophilic reagents. They are not electrophiles. Electrophiles are electron deficient species and nucleophiles are electron rich species. Since they are electron rich species, what? Alkenes. So that's why they are also known as electrophilic reagents, not electrophile, electrophilic reagents. Okay, so there exists one sigma and one pi bond in case of an alkenes. Okay, and alkene can also exhibit isomerism. Already we have learned same molecular formula but different structural arrangement is known as what? Isomer, and that phenomenon is called isomerism. Okay, so let's consider the example C4H8. So before that, what is the general formula of alkenes? Alkene which exhibit general formula CnH2n. CnH2n is the general formula of alkenes. And here C4H8, since 4 carbon atom, this is what? This is butane. Okay, so let's see the different isomers of butane first. So first one is this, a double bond is placed on the first carbon. Therefore, we can give the numbers 1, 2, 3 and 4. Therefore, this is known as what? But1ene. Okay, this is called but1ene. And here we can see when we will number this compound, the double bond is present in the second carbon. So this is what? This is but2ene. This is but2ene, or we can call this as 2-butene. Okay, or this is 1-butene, or this is 2-butene. A little more specifically, correct way of IUPAC naming is but1ene and this is but2ene. Okay, and now the third one. Here also we can find 4 carbon, 1, 2, 3 and 4 and 8 hydrogen. So 1, 2 and 3. When we will name the longest chain in this manner, double bond is present in the first carbon. That's why here we have given the number 1. So how we will name this compound here? So 2-methyl. The name of the compound is 2-methyl and the longest chain is propane. Propane. 3 carbon is present. So 2-methyl prop1ene. The correct name of this compound is 2-methyl prop1ene. Okay, so in these 3 cases we can see its name is different, but that is the structure is different, but the molecular formula remains same. So these 3 can be called as isomers of C4H8 or butane. Isomers of butane is these 3 compounds. So speciality of these 3 are same molecular formula but different structure. So they are also known as structural isomers. What they call? Structural isomers. These 3 are also known as structural isomers. Alkenes can exhibit one more type of isomerism, that is geometrical isomerism. For alkanes we have seen there exists only structural isomerism in case of alkanes, but here alkenes can show both structural and geometrical isomerism. So what is geometrical isomerism means? Same molecular formula but there exists difference in the spatial arrangement. Same molecular formula but difference in the spatial arrangement. So this geometrical isomerism, which is also known as cis-trans isomerism. Okay, this is also called cis-trans isomerism. Okay, so what is cis form and what is trans form? Let's see in detail. So here we can see a double bonded, an alkene is represented. General form of an alkene is represented, which contains 2 common groups or atoms. Okay, 2 common groups or atoms were attached to the C, double bond C, that is we can see 2X here and 2Y. Okay, so both are similar groups. So What is cis form means? If same groups are coming to the adjacent side, if same groups are coming to the adjacent side, that isomer is known as cis form. Okay, so here you can see X and X which comes on the same side, that is the adjacent side. So this is known as the cis isomer. Okay, and the next one you can see the same compounds or same groups are coming in the opposite side. If the same groups are coming on the opposite side, that isomer is called trans isomer. That is called what? Trans isomer. So when you are asked to draw the geometrical isomers of a particular compound, you have to draw cis form and the trans form. That is why geometrical isomerism, which is also known as cis trans isomerism. Okay, now let's draw the cis trans, or let's draw the geometrical isomers of these two compounds. And this is, we know this is what? This is 2-butene. The compound is 2-butene or but2ene. That is the first compound. So how we will draw the geometrical isomerism means, first condition in order to draw the geometrical isomerism, we need a double bonded carbon, then only it is possible. Okay, and at least 2 common groups. There we need at least 2 common groups in that. It is not necessary that the 2 groups, the 4 group, entire there exists 4 groups. Not necessary that the 4 groups must be similar, but at least 2 groups should be similar. Then only we can draw the cis trans isomerism. Okay, so here first of all we have to represent this C double bond C at the center. Here CH double bond CH, that comes in the center. So neglect the hydrogen and we can draw the C double bond C at the center. Now let's consider the species other than this C double bond C present. So 2 hydrogen atom is attached to this carbon. So that can be represented. 1 carbon to 1 carbon, 1 hydrogen, other hydrogen is to the next carbon. So which can be represented in this manner. Now to this carbon 1 CH3 and to this carbon also 1 CH3 is attached, and that can be represented in this manner. And here I have represented the same groups on the same side. That is why this form is known as the cis form, or correct IUPAC name of this compound is cis-2-butene. Cis-2-butene is the correct name of this compound. Now I have to draw the second geometrical isomer, that is the trans form of this compound. For that the same C double bond C should be represented, and 4 bonds where the hydrogen, that is the same group, should be on the opposite side in case of trans isomer. So 1 hydrogen should be here, next hydrogen should come here, then 1 CH3 and then to the opposite side next to CH3. So it can be named how? Trans-2-butene. The correct IUPAC name of this compound is trans-2-butene. Okay, so in this manner we will draw the geometrical isomers of given alkene. Center we have to draw the C double bond C, and then accordingly the remaining groups should be arranged around the corners of that 2 carbon atoms. Okay, now next let's draw the structure of this CHCl double bond CHCl. There exists CHCl double bond CHCl. So C double bond C should be represented at the center. Okay, so first C double bond C with 4 bonds, and then we can see to this carbon 1 hydrogen and 1 chlorine. The same groups is attached to the next carbon also. In order to draw the cis form, the same group should come on the same adjacent or same side. That means hydrogen can be given here and 2 chlorine atoms can be represented in this manner. Therefore, this is the cis form. Now we have to draw the trans form. For that again C double bond C, and the bonds where 1 hydrogen, if we will represent here, it should come on the opposite side, and chlorine also represent in the opposite side. Now we have to name this compound. Simply we have represented cis trans, but not so. Correct IUPAC name should be represented along with the prefix cis trans. Okay. So here let's see the IUPAC name of this compound. Anyhow, any manner we can give the number 1 and 2. Only 2 carbon comes. Therefore, in 2 carbon there exists what? Chlorine atom. Therefore, this is cis 1,2-dichloro. Okay, 1,2-dichloroethene. compound name is 1,2-dichloroethene. Since this is the cis form, we will add the prefix cis. Therefore, here we can write trans 1,2-dichloroethene. Okay. So this is the way how to draw the geometrical isomers, that is the cis-trans isomers. So please practice it with more compounds. Let's do more questions during the live session. Okay. So also the naming can be done during the live session. Okay. So thank you.